Today we're going to talk about change of basis. So last time we talked about the matrix of a linear transformation. So we have two vector spaces V and W, and we have a linear transformation from V to W. And what I'd like you to do is, even in the case when V and W are both Rn, a very familiar situation, try and think of a linear transformation sort of abstractly, not as a matrix, but just as some linear transformation from V to W. Maybe it's not given by a matrix, it's described in some other way. It's some abstract thing. It's not a matrix, it's a linear transformation. The point being that if you have a linear transformation, let's just talk about the case V equals W. That's the most common one. So you take a basis of V, and once you have a basis of V, then you can get a matrix. The matrix of this linear transformation with respect to the basis. If you chose a different basis, well, you'd get a matrix. And I'll write that as B prime. That's the matrix of T with respect to B prime. And the point I'm making is that the T is fixed. The matrix is varying. So the T is an underlying constant thing. It's only these matrices which differ. And we have, that is to say, there's two different matrices, but only one linear transformation. So I sometimes like to think of this as being a sort of ethereal T up here, which is abstract and fixed, and only when you have to choose a basis do you come down here with a basis B or B prime or B double prime. You get all these different matrices. These are all just manifestations or realizations of the same linear transformation, but the matrix itself depends on the choice of the basis. Okay, that's a summary of what we talked about last time. And what I want to talk about today is see how this matrix really does depend on the basis. If you chose two different bases, what happens? How are these matrices related? And this is the operation known as change of basis. So I'm going to illustrate this with one lengthy example. Let's take a map from R2 to R2, and let's take the following linear transformation. It's the one which takes E1 to 2E1 and E2 to E1 plus 3E2. So I'm intentionally writing these vectors as the standard basis, rather than writing them as actual n-tuples, just to help you think about these things abstractly. So what is the matrix of this linear transformation? Well, it takes E1 to 2E1 plus 0E2, so you make that the first column of the matrix. And it takes E2 to 1E1 plus 3E2, so that's the second column of the matrix. And, well, I could have started here. We're talking about the standard basis. I could have said, just take the matrix 2, 0, 1, 3. And it's the usual matrix. You know what I mean by that. And when you apply that to 1, 0, you get 2, 0. And when you apply it to 0, 1, you get 1, 3. This is just the more familiar way of writing these two equations. So I haven't done anything new. I'm just saying things emphasizing this basis here. And now I come along and I say, well, I'd rather you use a different basis. Let's use a new basis, V1 and V2, where V1, well, for V1 I'll just take E1, if you don't mind. But for V2 I'd rather take E1 plus E2. So what's the matrix going to be with respect to this basis? So we have to compute what is T applied to V1. Well, V1 is E1, so it's T applied to E1. And I already told you that's 2E1. Now, you need to write this in the basis of the V's. Well, 2E1 is 2V1. So that's good. What about TV2? Well, V2 is E1 plus E2. And when you apply t to that, let's see, TE1 is 2E1. So that's the first term. And the second term is TE2, which is E1 plus 3E2. So there you go. And let's gather these terms. That's 3E1 plus 3E2. Now I need to convert this back to the V1, V2 basis. What is E1 plus E2? Well, that's exactly V2. So that's easy. This is 3V2. Sorry, that's a misprint there. That's a V2. So here's my matrix. T applied to V1 and V2 are given and circled in red. So the matrix with respect to this basis is, well, I take 2, 0, and 0, 3. So there you have it. In the original basis, it was 2, 1, 0, 3. In the new basis, it's 2, 0, 0, 3. Okay. Well, that looked a little complicated, and I'd like to simplify it. So let's find a shortcut for doing this kind of calculation. So I'll remind you I had my E1 and my E2 and my V1 and my V2. And let's see, V2 was E1 plus E2. So what I want you to do is take the matrix S. And the matrix S is for the first column, you write the vector V1 in the original basis, the standard basis, and the vector V2 in the standard basis. So let's see, the vector V1 in the standard basis, well, that's E1. So that is to say it's 1, 0. And the vector V2, you look here, that's the coordinates, the coefficients are 1, 1. So this matrix S is right here, and it relates these two matrices. It has nothing to do with linear transformation. It has something to do with the way the matrices are related. And now here's the beautiful fact. S has the following nice property. If you take t in the standard basis and multiply on the left and the right by S inverse and S like this, it converts it to the new basis. So this S is called the change of basis matrix. And let's check. So S inverse is 1 minus 1, 0, 1. And I'm saying you take t in the original basis, which was this guy, 2, 1, 0, 3, and you multiply on the left by S inverse and on the right by S. Let's see what you get. Well, let's see. When you multiply this, you get 2 minus 2, 0, 3 times 1, 1, 0, 1. And what do you get? You get 2, 0, 0, 3. And there you go. I started with the matrix 2, 1, 0, 3, and it converted it to the matrix in the new basis 2, 0, 0, 3. Well, how does this work? Let's just unpack that and see what makes this tick. So again, I started with the standard basis and this new basis. And what's the point is what's the meaning of this matrix S? What does this matrix do? Well, the key is that S has the following property. If you take a vector and you write it in the new coordinates and you multiply it on the left by S, you'll get the vector in the standard coordinates. It's the change of basis matrix. So let's check. If you do this multiplication, you get 1, 0. And what this says is that this is the vector v in the original basis, and it's the same, it comes out the same, 1, 0 in the standard basis. But let's look at the second vector. Let's see what you get there. So if you multiply this matrix, let's see, if you take this vector in the standard basis, excuse me, in the new basis, 0, 1 is this vector v2 in the new basis, you get v2 in the standard basis, and that's exactly correct. This is the thing which says v2 is e1 plus e2. And this previous line is the thing that says V1 is equal to E1. So this is the key property of this matrix. It changes the coordinates of a vector from one basis to another, and it's obviously, that's why it's called the change of basis matrix. And, well, that's what makes this formula work. What happens is I have the matrix T in the new basis, and I'm claiming that it's related to the matrix in the old basis by this formula. And the reason is, let's look at this right-hand side, S inverse TS. If you take this and you apply it to a vector, well, what kind of a vector are you going to apply it to? You're going to apply it to something in the new basis. Well, the first thing when you multiply is this S comes first. That's going to convert it from the new basis to the original basis. Okay? And then you're going to apply this matrix T, and it's correct. It's the right basis. It's T in the standard basis, so it's going to take V in the standard basis to TV in the standard basis. Good. And now the last thing is S inverse. Well, that goes back. It's going to convert this from the standard basis to the new basis. And so if you do all three of those, that's the same thing. This map here is exactly T in the new basis. So let's just see how this works in our example. Let's take V, for example, to be V1. Well, that's in the new basis, that's 1, 0. And let's apply S to that. And that's going to take it to 1, 0. And then let's apply T in the original matrix T in the standard basis to that, and we'll get 1, 0. Excuse me, 2, 0. And then when we apply S inverse, we're going to get 2, 0. And on the other hand, when we do V2, which is 0, 1, this S is going to take you to 1, 1. And then T takes that to 3, 3. And this S inverse takes that to 0, 3. And that's the correct result. This 2, 0 and 0, 3 here are what are telling you that this matrix is diagonal with 2 and 3 on the diagonal. So this little calculation that I did here is the shorthand for the way I sort of worked it out by hand earlier, and it shows you that the matrix S is taking care of that for you. Okay, so here's the theorem. Suppose you have a map from V to V. I'm just going to say it for a single vector space, and you have a basis B, which you're using on V. And let's say you write that basis V1 through Vn. And you have the matrix of the linear transformation. It's an n by n matrix with respect to that basis. Now you come along and you choose a new basis, W1 through Wn. And I'd like to know what the matrix of T is with respect to this. Well, you take the matrix S, which is you take these vectors W1 through Wn, and you write the coordinates in the original basis. So that is to say, W1, for example, it's some vector. Well, you write it as a linear combination of the original basis, A1 through AN. You make that the first column. And similarly, you write W2 as a linear combination B1 through Bn. And that's your second column, and so on. You get an n by n matrix this way. And then the theorem says that the matrix of T in this new basis is given by S inverse times the matrix of T in the original basis times S. This is the change of basis formula, and we're going to be using this quite a lot from now until the end of the semester.